In this video, we will solve probabilities involving all, none, or at least one in their description. So what does that mean? Well, let's take a look at example 1. In example 1, 6.6% of Americans have O negative type blood. This is a kind of blood type. Suppose we select a random sample of 5 Americans. What is the probability that all of them have O negative blood? Or what is the probability that none of them have O negative blood? What is the probability that at least one of them has O negative blood? So these are 3 different events that can be described in the context of selecting 5 Americans. So, first, some preliminary observations. If we select one person at random, just one, not 5, then there's a 6.6% chance that they have O negative blood. Something when we're thinking about an event that's about does this person have a certain characteristic, one thing we might want to do is think about also what is the probability that they don't have that characteristic. And we can use the complement rule. 6.6% of Americans have O negative blood, which means that 93 point... sorry, I calculated that earlier. 93.4%. So 6.6% of Americans have O negative type blood, which means that 93.4% do not. And I'm writing my percentages as decimals, as you should always do when you're computing probability. Another thing we want to think about is let's think about selecting our sample of 5 Americans. If we select the 5 Americans, we're probably going to select without replacement, which means that the selection would be dependent. That the first that as we select each of our people into our sample. We're changing the pool, we're changing the population that we're selecting from. And so that would cause a change in the probabilities as we move along. And you've probably worked with some probabilities involving the multiplication rule using conditional probabilities. And that's what we would have to do with the dependence. However, because the pool that we're drawing from is very large, there are 350 million Americans out there to choose from. As we select one American and then another and then the fourth and the third and the fourth and the fifth, we're not changing the population that much. Taking one person out of a very large population like that, or even taking 5 people out of a very large population like that, doesn't change. And so the dependence is very weak. And so it's actually the calculation that we would do if we did this carefully. We would need to know the exact population size, and we don't have that information. And it's actually safe to assume that we're drawing independently, and so we don't need to think about the conditional probabilities. This means that, in particular, that we will be able to use the special case of the multiplication rule when it comes down to it. So let's look at the first problem. What is the probability that all 5 of the people in our sample have O negative type blood? And so what I'm thinking about here is, as I select my sample, I can create these little these lines here, these boxes to put the person in, to put each person in. So here's where the first person is going to go, then the second person will stand over here, and the third, and so on, in these slots. Now, if this event is going to occur where all 5 of our people in our sample have O negative type blood, that means that we want the first person to have O negative blood, and the second person must have O negative blood, and the third person, and the fourth person, and the fifth person. Notice the repeated use of that word and. I wrote it here for highlighting. So remember, and is going to tell us that we want to use the multiplication rule to compute probability. The independent says that we can use this special case, which means we just need to think about what is the probability of the first event occurring in the second. So what is the probability that the first person has O negative blood and the second person has O negative blood and the third person? I don't need to worry about what happens, what's the probability of the second person having O negative blood given that the first person has O negative blood. And so when I want to compute that probability, I'm going to multiply the probability that the first person has O negative type blood, that's 6.6%, 0.066, times the probability that the second person has O negative blood, another 0.066. The probabilities are not changing as we move along, as long as we're assuming independence. Now, if I multiply 0.066 times 0.066 times 0.066, that's repeated multiplication, which is where exponents come in. And so I can write that probability as 0.066 to the fifth power. And I calculated that ahead of time, and you can see this is a very small probability, 0.0000125. Very few people, 6.6% is significant, but it's not a very, very large percentage of the population. And to have all five would be very, very restrictive. All five of our people in our sample having O negative blood, that's a very restrictive event. And so very few of our 5-person samples would have that event. Now's a good time to press pause for understanding. In fact, I'm going to give just a couple seconds at the end of each of these parts to allow you to pause, reach the pause button, and just look at the solution for a little bit, write some notes. Okay, let's look at the next one. What is the probability that none of them have O negative blood? Well, this is also kind of restrictive. If you think about it, I'm going to just go ahead and start computing the probability. I like my little line diagrams for this. And I'm just putting a little quick description of the event I'm looking at. So again, we're selecting 5 people at random. And we want the first person to not have O negative blood. We want the second person to not have O negative blood. And the third person, I'm just going to put a ... We want not O negative all the way across. And so what's the probability that the first person doesn't have O negative type blood? That's going to be 1 minus 0.066. Yeah, I know, we found that was 93.4%. And then the second person, the probability that the second person doesn't have O negative blood is also 1 minus 0.066. And the third person, 1 minus 0.066. Fourth person, 1 minus. And the fourth person, I'm having a little bit of trouble fitting this on there, in my lines, but you can draw more carefully, but you get the idea. And so what's the probability that none of these have O negative type blood? It's going to be this product. I'm not evaluating the 1 minus 0.066 yet because I want to make a point about how the calculation looks relative to the original percentage. So that's going to be 1 minus 0.066 to the fifth power. And so what you'll notice is that in the base of this exponent, the 1 minus 0.066, that's the probability that one person, that if we select one person at random, that they don't have O negative blood. And then we're taking that to the 5th power because we have 5 people we're considering. And again, I computed that ahead of time. It's a larger probability. It's still restrictive, but again, well, 93.4% of our population does not have O negative type blood. And so you can see that the base is considerably bigger than the base that we had in the previous example. And so when I looked at that, I had, I'm not going to copy down the whole thing. Maybe I'll round to 5 decimal places, say 0.7107. 078. Pause for understanding again, pause the video, and take a look at this solution here. Maybe work it out for yourself. Make sure you agree with me. Okay, let's look at the at least one. Probability that at least one has O negative blood. Again, we'll lay out our slots for our 5 people to stand on. Now, if I want at least one, I want to make sure that one of these slots contains someone who has O negative blood. So we could put that that O negative in the 1st slot, or the 2nd slot, or the 3rd slot, or the 4th slot, or the 5th slot. And for that matter, we could actually have 3 of these people have O negative blood, and that's still at least one. At least one means 1 or more. So again, we want to know the probability of having the 1st person have O negative blood, or the 2nd, or the 3rd. That or hints at an addition rule, but it's more complicated than that because we only know how to find the probability of A or B. These are not mutually exclusive events. Again, we could have both the 1st person have O negative blood and the 2nd person have O negative blood, and that would still fit in this event. So we don't have mutual exclusivity to help us with this OR calculation. So instead what I want to do is I want to think about how could we make this more restrictive. So let's consider the event E. Let E be the event that we get at least one O negative person in our sample. I think of this as a blood donation thing, maybe. What would the event not E be? Let's think about this. Let's think about how many O negative people could be in our sample. Well, let's see. Maybe none of our people have O negative blood. In fact, we found out that there's a 71, almost over 70% chance that none of our people have O negative blood. That would give us 0 O negative blood, people with O negative blood in our sample. We could have 1 person in our sample. Just put 1 person in either one of these and then fill the rest with non-O negative blood type folks. We can have 2. We can have 3, 4, or 5. If we have 0, that's amounts to none of our sample has O negative blood. 5 would be all. Now, what we want is we want at least 1, which means that the number of people who have O negative blood should be 1, or it could be 2, or it could be 3, or it could be 4, or it could be 5. So one thing to note is that if I take away all of the at least 1 possibilities, the only possibilities I'm left with are the none. And so what the big observation that I want to make about this problem is that the complement of having at least 1 O negative blood donor is actually none of O negative blood, people with O negative blood in our sample. None of our sample has O negative. And so we've got, that lead is getting me. We've got the event E that we want. We want to know the probability of E. But we can write the probability of E using the complement rule as 1 minus the probability of not E. So the probability of at least 1 is 1 minus the probability of none. And so this is a key observation for this type of problem. If I want to know the probability of having at least 1 of my people have a particular characteristic, I can find the probability that none of them do, and then use the complement rule. And so, but we already computed this. We computed this one in part B. So let's go and look that up. This is 1 minus I'm going to go and take the that original version of this probability. So that was 1 minus So this looks complicated where we ended up, but we can see that in order to have none, we want to make sure that each one of our the 5 people in our sample falls into the category of not having O negative blood. So that's where the 1 minus 0.066 comes from. The 5th power comes from making sure that we want none of our people to have O negative blood. And then, so this 1 minus 0.934 to the 5th power, the 0.934 to the 5th power, that tells us the probability of none of our sample having O negative blood. And then the 1 minus is computing the complement of the none event. And the complement of none is at least 1. And I got a calculation for this one as well. This is a pretty powerful technique for, in particular, finding what is the probability of getting at least one, say, success. If you're playing a game and you're trying to get a success, for example, maybe we are randomly selecting or treating 5 people lined up for a blood donation as independent of one another, as an independent sample. if we can treat that way, then we might want to know, hey, if we're looking for O negative blood, the blood bank is low on that. We want to know, like, what's the probability of getting at least one sample of one donation of O negative blood. So that would be an interesting one. Another possible example might be winning the lottery. You only need to win the lottery once, right? Speaking of which, what if I wanted to? What if I had a larger sample? Well, looking at this simple example, where we could list out all of the individuals, I could go ahead and think about what is the probability of getting at least one AB negative blood donor in 500 in a sample of 500 Americans. AB negative is rarer. It looks similar, but it's less than 1% of Americans have AB negative blood. And so I would like to know the probability of getting at least one. I know that the probability of at least one is 1 minus the probability of none. AB negative. I know that's not English. Okay. So let's look at the probability of none. Now, where we used to have a sample of 5 people, now we need to have a sample of 500. First person, second person, third person, 500th person. So I can't write that out all. I don't want to take that time. But what we can do is we can look at, okay, what's the probability of, let's see, the probability of not AB negative with one person is 1 minus 0.006. That's what a 0.6%, 0.6%. So that's going to be 0.994. So I'm going to put 0.994 times 0.994 times 0.994. How many 0.994s do I have? Well, one for each person in our sample, and so that's going to be 0.994 to the 500th power. Notice that that's using the original percentage, the percentage of people who have AB negative. That would be 1 minus 0.006 to the 500. And I've got a round off of that. That's going to be, it's almost 95. Oh, sorry. I'll leave that at B. Now, the probability of at least one. AB negative person in our sample is going to be 1 minus 0.994 to the 500th power. The 0.994, that's the probability that someone doesn't have, that one person randomly selected doesn't have AB negative blood. The 500th power is because we are selecting 500 people. And the 1 minus 0.994 to the 500. And this is where I have a 0.95066. So there's a pretty high probability, even though the AB negative is rare. There's still, we expect to get, we can reasonably expect to get at least one AB negative donor in such a large sample. And again, I'm thinking in terms of blood donors. So again, pause for understanding, and maybe think about other ways in which this technique could be applied. Blood donation is, blood type is one thing, but Again, this could be applied to playing, gambling. And if you play the same game over and over again, and the probability of winning that game each time you play is a certain amount, you can think about what's the probability of winning at least once. Any characteristic we have in the population. This comes up a lot when we talk about percentage type categorical variables. Any sort of category you want to look at. This could be blood type. This could be political opinion. What's the probability that we find at least one person in a random sample of voters who's going to vote a certain way? So this gives us how to find the probability of all of our individuals having a certain falling in a certain category, none, or at least one.